Okay, so now we're in our Data Hub notebook, sampling distributions and the Central Limit Theorem, and a lot of the things that we just discussed are listed here. Okay, um, and what are we doing? We have some data frames that we can sample from later, and we also have three sampling functions that we're going to use. Rflip, which simulates the binomial distribution. That's the first one we're going to use. Rspin simulates a spinner, which allows us to do a lot of different things. A lot of different probability distributions can be set up that way. Why? Because the spinner can be any number of slots, and each of the slots can be any probability that we desire, as long as all the probabilities sum to 1. Okay, and then sample.data.frame is the one we're going to use to sample from one of these data frames. Exactly as it sounds, sample.data.frame. Okay, so first we're going to use the rflip function, all right, and we'll initialize it here and make sure that it's ready to go. Okay, I'm just checking to make sure that the data frames are loaded. And then here is this for loop that I showed you on the slide. And notice that there are some hints, some notes, right? These comments here to help you see what each line is doing. Now, I went through it without the notes to kind of show you what's going on here. All right. And I had a lot of equal signs where I'm using the arrow. It turns out that the left arrow is more correct in R. Okay. And when I run this for loop, notice what I see, right? I am seeing the grand mean from all the samples. I'm seeing a blue line at the 5th percentile, a blue line at the 95th percentile. So I'm seeing the middle 90% of this histogram, right? And the histogram was using sample size 50 and a probability of 0.25. By the way, the expected value for the binomial distribution is NP. Okay, so here we have the sample size n times the probability p, which is about 12 and a half. And I'll write that over here. Why? Well, because the grand mean is going to be an estimate, right? And you notice that 12.383 is quite close to 12.5. And our sample size was only 50. Okay, so what are we going to do? Well, of course, we're going to do the exact same thing, but increase the sample size. Let's try a sample size of 100. And okay, I've got to get back so I can do what? So I can copy this, and I'm going to paste it. And what am I going to do? I am going to change the sample size from 50 to 100. Okay. Oh, and the experiment that I said we were simulating is that we're in an M&M factory and there's a big giant vat that collects all the candies. Each line is monocolored, right? And then there's multiple colors in this big vat, and if you draw some, you've got a 25% chance. I mean, there's millions and millions and millions of these different colored candies, but what you're going to see is that if you draw these samples, you're going to repeatedly get about 25% red. All right, so that's what we're doing, and that's why it's saying candies here, right? Red candies. Okay. And so in the main title of the histogram, I'm going to switch to 100, right? Switch to 100 here, switch to 100 here, switch to 100 here. Okay. And then run it. Okay. And notice what? Well, okay, so n equals 100 probability. So we know that the expected value is 25. 100 times 0.25 is 25. And notice our sample size has increased to 100, and we're very close, right? We're getting closer. Our grand mean is much closer to mu. All right. So what are we going to do? Well, let's increase it again. Let me copy paste. Okay, and what are we going to do? How about, oh, let's cut to the chase. Let's try 500. Sample size 500, 500, and then the main title will be 500. And I'm looking to make sure that everything else is correct, and it is. Okay, and then I run it. And notice how quickly that does it. It's drawing a sample of a size 500 1,000 times, and it did that in like half a second. And notice that if n is 500 and p is 0.25, right, the mu, right, based on the expected value of the binomial distribution being n times p, we know that the expected value is 125. And we are getting 124.609, which, by the way, isn't quite as close as we were last time. So this is a limit idea, as the limit as n as the sample size, which we said on the earlier slide was k. But as the sample size grows larger, right, this grand mean will get closer and closer and closer to mu. Now, it's not a linear, always getting closer sort of thing, but in the limit, it does eventually get exactly to 125. Okay? So that is a sampling distribution, and hopefully you're seeing the central limit theorem in action there, right? That as the sample size of each sample increases, right, this grand mean becomes a better and better estimate of mu, the actual average of the distribution. And what are we noticing about these bell shapes? Well, they get narrower and narrower, right? Because that sample size, the square root of the sample size is in the denominator. So the histogram is getting narrower and narrower and therefore becoming a better and better estimate. All right, so that seems pretty clear cut. And now we're going to do some work with this sample.data frame. So let's just run this to make sure that it's good to go. And then what I'm going to do, I'm going to take this and copy paste it, but I'm going to have to fix it a little bit to work with this narcissism vector, right? Number of successes is fine. Number of samples will be fine. Even though there are only 140 roughly in this data frame, 140 individuals in the data frame, we can repeatedly sample as long as our sample size is less than 15%. So we need to draw only 15 to 18 is about the max that we're allowed to draw. Okay? And we're not going to do our flip. Okay? We're going to use our sample data frame, sample.data.frame, and I'm going to show you that that command in just a second. Let me show you how that works. Okay, so what I've done here is I have changed this part of the for loop right here. Okay, and to show you what's happening, I have the piece of it down here, the sample.dataFrame function, the name of the data set, the size of the sample to be drawn, and original IDs equals false. There's it kind of basically takes a row number from the original data set, and all it does is it just messes up our ability to read it as a data frame. We switch into row column notation to get the narcissism column from the sample that we draw. And then we can take the mean of it. If you see the mean function here, surrounding this whole thing. But let's see how this piece of it works. Right, let's just run this. And you see that it's drawing a sample of size 10. And it's just a numeric vector, right? So I can take the mean of it, right? The mean will work just fine. Right, let me jump in here and type mean, and then close the parentheses, boom. And so there's one draw. We draw 10, and the average narcissism from those 10 is 3.8. And then the next 10, we have an average of 4.9, and then 4.5, and then 4.2. And I'm hitting Control Enter so that I'm repeatedly evaluating this sample.data frame and the average. And you see that the values are all bouncing around, the fours, 4, 4.5, 5, in that range. Okay, so what are we going to do? We're going to do it 1,000 times. And let's start with a sample size of 5. And at the moment, we're drawing 5 samples, or drawing a sample of size 5. Draw sample of size 5. All right, I'm not going to fix all of the notes because we're doing the same basic thing as before, and you can fix your comments to make them more appropriate to this. Okay, we're still going to calculate the percentiles from the number of successes. We're still going to print out the average number of successes, which is the grand mean. We're also going to print out the histogram, and our sample size is 5. And we don't know our probability here, right? So let's say this is a histogram of narcissism for a sample size of 5. Okay, and I think that's all the tweaking I want to do to this for loop, and then I'm going to run it, and P is not found. Okay, so I changed the name of the personality data set from pers to P, and so if I just jump back in here and change this value right here from P to PERS, now we're working. Okay. Okay, so you see that we have the same thing as before. We have our 5th percentile and 95th percentile vertical lines in blue. So we see the middle 90% of this distribution is between about 3 and 7. Those are approximate values, right? And I can play around with the number of breaks in the histogram to see if I can get a better picture of exactly, what's going on there. I'm not going to bother with that right now because this is very good. Notice that the average, right, this is the grand mean, the average of the averages is 4.725, okay? So that seems good. And we can do a little more. Remember, there's only 140 or so in the personality data frame. Okay, so we're going to want to not go too high with the sample size. 15 is going to be about the most we can squeeze in there. All right, so I'm switching from a sample size of 5 to a sample size of 10, and I'm running the same thing. Okay, and now notice, right, that our grand mean is 4.7, and we have a nice bell shape that is getting narrower. We see the middle 90% is getting a little closer, right? We're about 3 1/4 and just higher than 6, so we've got a narrower bell curve, and we're getting a better estimate, and we can only do about one more, right? So we said that 15% of the sample size allows us at most about 15 or so. So I'm going to run this again with sample size 15. So copy pasted everything 15, and this is sample size 15. Okay. And you run it again, and we get 4.69 as our estimate. And you see that we also have a bell curve that's getting narrower, right? So now we're up above 3.5. This is maybe 3.6, and we're less than 6 up here. So notice how the the bell curve is getting narrower and narrower. That's why the mean, the estimate of the mean, mu, is actually going to get better, right? The narrower the histogram, the more accuracy we have. Now, this is a situation where the sample size just has a limit on how big we can make it. We'll be oversampling at more than 15 or so, right? So we're kind of at our limit here, but we can use the law of large numbers. And It is not lost on me that law of large numbers acronym is LOL. So we will use the LOL function or the LOL theorem. Why? What are we going to do? Well, we have a limit on K, the sample size, right? This can't get any bigger, but this can. Okay, let's do 5,000. Okay, what are we doing? Well, you're saying, well, there's only 140 things to draw from. Yeah, but if we're only drawing 15, we can draw as many times as we want. In other words, the values will appear in more than one sample. And that's fine. It's called resampling, and that's fine. I'm going to use a sample size of 5,000. And let's see, not sample size, I'm sorry, number of samples. Let's do that. Let's say samples equals 5,000 as a title up here. We'll just say that we're increasing the number of samples. We still have the sample size of 15, but we're increasing the number of samples. Now it's taking a little longer. Why? Because it's drawing samples of size 15, but it's doing it 5,000 times and then drawing the histogram and then calculating. All right. And notice that we're getting an even better picture, a narrower histogram. The histogram is looking more and more bell-shaped, right? So the law of large numbers is helping us out here. Okay, and just as a last thing, we can do this. We can just say, what is the mean of the personality data set narcissism vector? And the mean was actually 4.6899, right? And you'll notice 4.677. So we were getting a really good estimate. And notice how when the sample size is limited, right? I'll be oversampling if I have a sample size larger than 15. I can just take more samples. And the law of large numbers helps me when the central limit theorem can't get me the level of accuracy that I want and need. Okay, so one more example, United flight delays. Okay, and so let's do this. This is United. And I believe, let me try this. It doesn't like it. Maybe it's capital delay. There we go. So that's the grand mean that we're aiming at. We're aiming at 16.658. What are we going to do? We're going to do it using sampling distributions. First of all, right, I'm going to fix this. We're going to do the United sample, and we're going to take the delay. And let's start out with 50. It turns out that there's like 14,000 or 40,000. There's a huge number. Let me try this. Let's look at the sample size of this thing, because there's a bunch. Okay, yeah, almost 14,000. All right, so we'll be able to take samples of size, well, 1,400, right? We can take samples of size 1,000 and still be less than 10%. Okay, so I'm jumping back to the mean so that we know what we're shooting at. What am I going to do? Well, I'm going to start with 1,000 samples. And what sample size I'm going to use? I'm going to use 50. Okay, so sample sizes of 50. And I'll use, n equals 50. All right. And I believe I have everything fixed, right? So we're sampling from the United data frame. The delay column is the one that we're trying to estimate the average of, right? This one. Okay, and it's not narcissism, it's histogram of delays. Okay. Okay, so we were shooting at 16.658, and you'll notice that we did okay. 16.79. We have the middle 90% showing here between about what? 9 minutes and 27 minutes. I mean, that's just a guess. We could get the actual values if we wanted to. Okay, But again, we have a lot of wiggle room here, right? Because there's so many samples, right? So I'm going to copy paste this, right? And since we can go so large, let me try 500, a sample size of 500 right away. And I'll put that down here, a sample size of 500. So 1,000 samples of size 500. Okay, and run that. And look how quickly it does 1,000 samples of size 500. And notice, right, that we're getting 16.63, which is pretty close to what we're looking for. Also notice that the middle 90%, right, between the 5th percentile and the 95th percentile lines that I've drawn in there is between about 14 and what, 19 and a half, I guess. So the delay for these United flights on average is between about 14 minutes and 19 and a half minutes, which makes sense. Okay, and we're doing well with our estimates. Let's do this one more time. And let's have sample size 1,000. Okay, and the sample size 1,000. And let's just run it. Okay, and you'll see 16.6711. Do you remember the target we were shooting at? Let's just roll back up where we did this, right? Oh, sorry, where we did this. 16.58. I'm going to actually bring this down where we can work with it closer to where it was. Okay, so 16.581, right? And we're at 16.677. So we've clearly gotten within a couple hundredths. We're within a couple hundredths of the correct value. And we have a narrow bell curve. The bell curve is very symmetric, very bell-shaped. So the bell shape is improving as the sample size increases. The bell curve is getting narrower and and becoming a more accurate estimate as the sample size increases. So again, you're seeing the central limit theorem at work here. And in the second example, we showed that when we run out of room to work with the central limit theorem, we have the law of large numbers we can invoke. Okay, so this is just 3 quick examples showing you how sampling works, right? How it is that we get these bell-shaped distributions, how we get better and better accuracy with both the central limit theorem and the law of large numbers. Hey everybody, so we're here to talk about the central limit theorem, and this is really the theory that holds statistics together, that makes the transition between probability and statistics, and it relies on a thing called sampling distributions. Okay, so what are we talking about? We're talking about taking repeated samples of the same size from the exact same population. Okay, and when we do that, we have what we call a sampling distribution. Okay, so to make it a little more clear, right, we have a set of samples. We have n samples, okay, and the mean of sample capital X sub 1 is little x bar sub 1, okay? And we're having the same sample size for each of the samples. The sample size is k, so the number of samples is n, the sample size is k, right? And the sampling distribution is the set of all the means from these n samples, okay? So if I make a sample of all the means from each of the individual samples, that's a sampling distribution, and this turns out to be bell-shaped, okay? So that's the key that's going on here, that we will end up with a normal distribution, okay? Also, just to let you know some symbols that we'll use. The grand mean, bar x, is the mean of all the sample means, right? So if I take the average of all the x sub I, x bar sub i's, right, then I have the grand mean, which is the average of the averages. Okay. So the central limit theorem says that when I have, and this is just describing a sampling distribution, right? These first two lines are just describing a sampling distribution, right? And the population that's being drawn, the samples are being drawn from, has a mean mu and a standard deviation x. And as the sample size grows, this sampling distribution can be assumed to be approximately normal. Specifically, this is the distribution. So a couple of things here. First of all, the capital N with the parentheses is the way we refer to a normal distribution. And in statistics, normal distribution and bell-shaped distribution are the same thing. They're synonyms. Okay, and this is saying that, hey, we're going to have a bell-shaped distribution, a normal distribution with average mu, which is good. That's the original population average. So the samples that we're drawing are also going to be a good estimate of mu. They're going to get closer and closer and closer to mu as k gets larger. Okay? And the standard deviation will be sigma over the square root of k. What's notable here is that k is in the denominator. So as k grows large, right, the bell shape gets narrower and narrower. It becomes a better and more accurate estimate of mu, right? The grand mean is going to trend towards mu as k gets large because the bell shape of the sampling distribution gets narrower and narrower and narrower. All right. And also we have a limit on the central limit theorem, right? Our sample size can't grow unbounded in certain cases. If we've got a population, let's say UNG Dahlonega, let's just say there are 7,000 undergraduate students, that's about right. We should never sample more than 10 to 15% of that 7,000. Well, okay, so we can have 700 to 1,000. By the way, the 10% is quite conservative, and that's generally good. 15%, you will hear some authors allow up to 15%. But everybody agrees that you go above that and you are oversampling, okay? And that can cause some problems. So when we're doing this process, we want to make sure when we're drawing from a regular distribution, from a data frame, for example, that we're not using more than 10 to 15% of the population size, okay? Another lever we have for accuracy is the law of large numbers. And the law of large numbers applies more widely than just statistics, but it says that when we're making an empirical estimate, the accuracy improves as the number of trials grows large. Okay, so the central limit says, hey, as the sample size gets bigger, we get more accuracy. However, the law of large, that's again, sometimes there's a limitation on how much work we can do with k. But the law of large numbers, we can take more and more and more and more samples to get more and more and more accuracy. Okay, so the central limit theorem and the law of large numbers allow us to get really good accuracy as our grand mean, bar x, right? It goes to mu. So our estimates from sampling get closer and closer to the actual average. Mu is the actual average. Okay, and this is it in a nutshell, right? That I can keep taking more and more and more samples. And as I do, my grand mean is getting closer and closer to mu. Okay, and like I said before, the law of large numbers applies more widely than just statistics, right? But this is one of the things that really helps us in statistics. Now, the next question is, well, where do these sampling distributions come from? And it turns out that I can do empirical estimates of the probabilities and the expected values, for example, of all those discrete probability distributions that we looked at in the probability section, the binomial distribution, geometric, negative binomial, and hypergeometric distributions. In other words, we can simulate them multiple times. Okay, so that would be n increasing. We can also take large samples, right? The binomial distribution, we can have a sample of size 50 or size 100 or size 1,000, right? Why? Because it just requires running a loop in the computer multiple times, okay? So we can see the central limit theorem working in these situations. One way we'll use it is we'll draw repeatedly, draw samples from a data frame. And that's a lot more similar to how the central limit theorem and the law of large numbers actually apply to statistics, okay? And as we go forward, we're going to need these for loops, right? The loops are going to be what run these simulations multiple times, all right? So you see the number of samples, right, is set at 1,000. The number of successes, what's this? Well, the number of successes is using the concatenate function, but it's empty, right? So what's this going to be? This is an empty vector. Why? Because it's going to be where we store all the successes, and it's going to be the thing that we use, right, to report on all of our successes. We'll make a histogram of it. We'll take the mean of the number of successes, and we'll be able to find the percentiles, the 5th percentile and 95th percentile. So we can use them to draw lines. So let me kind of go through more of this. Something that's good to notice is that the for loop, the stuff that's going on inside the for loop, is put in curly brackets, okay? You see inside the parentheses, this is the indexing variable. So I is the indexing variable, and it's going to go from the value of 1 up to the value of number of SAMPs, which in this case is 1,000. The reason we use a variable here for number of SAMPs is so that all I have to do is change this and change this value from 1,000 to 10,000 or 5,000 or 2,000, right? And rerun the for loop. All right. This rflip function, okay, what's it doing? rflip simulates the binomial distribution with probability 1/4, right? The summarize equals true makes a little data frame, so we can switch to row column mode inside that data frame to grab what? The number of successes, okay? So we're flipping a coin 50 times. The chance of heads, or the chance of success, is 1/4. We're putting the summarize equals true so that I can use this data frame row column notation to pull out the number of successes out of the 50 trials and store it in here. Okay? So what happens is as this loop repeats, right, this vector goes from being empty at the start to having 1,000 values in it, the 1,000 values that are the number of successes out of 50 that we're seeing in each of the 1,000 simulations. Okay? Lower is a variable name that we're assigning to the 5th percentile of this num successes vector, and upper is the 95th percentile. Notice that we're using those percentiles to draw these lines. The lines are going to be superimposed on this histogram. The histogram is going to show the distribution, the sampling distribution, and we're also going to print out the number of successes, the grand mean of the number of successes. All right. So that's what we're doing in the for loop, and I just wanted to go through that before we jump into the notebook. Why? Well, because we just have this code and it appears from nowhere. So I wanted you to understand what's going on with this code, right? We have the for loop here. We have the percentiles calculated here. We have a print statement or a cat statement with the average, the grand mean printed out, and then a histogram with these lines drawn at the values lower and upper, which are the 5th percentile and 95th percentile. So let's jump into the notebook and do some examples.